In this video, we're going to review our oxygen binding curves for our two main oxygen binding proteins, myoglobin and hemoglobin. Myoglobin is our protein responsible for storage of oxygen. It is a monomer that has a single oxygen binding site. Therefore, there's no cooperativity, so we see this hyperbolic oxygen binding curve. Hemoglobin is our main protein that's responsible for transporting oxygen in the body and delivering it to the different tissues. It is a tetramer that has multiple oxygen binding sites, so therefore it does exhibit positive cooperativity and has that sigmoidal S-shaped binding curve. We'll note that at high oxygen pressures, we see similar affinity or binding capacity of both myoglobin and hemoglobin for oxygen. However, at the lower pressures of oxygen, you'll see that myoglobin has a higher affinity for oxygen than hemoglobin, as noted by the left shift in the curve. So this cooperativity that we have or that we see with hemoglobin does allow or enable hemoglobin to effectively transport oxygen and deliver it to the tissues. So if you subtracted the difference of the myoglobin bound in the lungs versus tissues, you could see myoglobin would not be an effective transport protein, as only 7% of the oxygen is released at the partial pressure in the tissues. In contrast, our hemoglobin is able to deliver 66% of its oxygen at the partial pressure found in tissues. So what we've talked about in class are different factors that can alter the oxygen release from hemoglobin. One of these was known as the Bohr Effect, and what the Bohr Effect states is that both carbon dioxide and protons are going to promote the release of oxygen. So release, remember, this means weaker affinity. So we're seeing a shift to the right. I won't demonstrate because if I point right, it's left on the screen. So what we're looking at here are three different curves that are going to demonstrate the Bohr effect for us. The first curve, A, is the main magenta curve there. It's the furthest to the left. That is oxygen release or oxygen binding to hemoglobin at pH 7.4 with no carbon dioxide. So what we're going to do is compare what happens, and we said that gave us a 66% release. That was the same curve we just looked at. We had a 66% release of CO2 or of O2. If we lower our pH, so we're increasing our proton concentration, we get curve B. So we have gone from pH 7.4 to 7.2. We get a shift to the right in our curve, right? Weaker affinity, we have more oxygen being released, and the actual amount there is 77% released. And then in our last curve, what we're going to do is we're going to keep our pH the same at that reduced 7.2, but now we're going to throw in some CO2. And when we do that, we get a further shift to the right in our curve. Again, that's a weaker affinity, causing the release of our oxygen. And at this point, we're up to 88% released. So that's what these, the type of shifts you'd expect in the curves, looking at changes in our carbon dioxide and proton levels. So both of those, again, if we increase our CO2 concentration, increase our proton concentration, which means lowering pH, we're going to shift our binding curve to the right. So we've just covered these two factors, our proton and CO2 concentrations. The other factor we talked about that can also decrease oxygen affinity or promote its release is the small molecule 2,3-BPG that also is capable of stabilizing the T state of hemoglobin, resulting in that shift to the curve to the right. Things that can have the opposite effect, which actually will increase our oxygen affinity or impede the release of oxygen, are fetal hemoglobin, and that's due to really a decreased affinity of the fetal hemoglobin for that 2,3-BPG. High pH is just the opposite effect. That's working with the kind of anti-Bohr effect. And carbon monoxide. So that will increase carbon monoxide hemoglobin will increase our oxygen affinity at the other sites, resulting in a shift to the left. So shifting to the left, lower KD value, higher affinity. So if we take a look at some additional curves here, we're going to state that our curve 3 is representing our normal hemoglobin at physiological concentrations of carbon dioxide, 2,3-BPG, and pH 7. What we're going to do is walk through the different curves, trying to revisit these concepts and showing just on a different graph what happens to our oxygen binding and saturation curves. So we'll just say curve 1 represents a loss of quaternary structure. So if you compare curves 3 and 1, you'll note that curve 1 is more of a hyperbolic curve. That's what we saw with myoglobin. So if hemoglobin were to lose its quaternary structure, you'd no longer have that cooperativity, and so you'd have that hyperbolic curve 1. Note that does also have enhanced or increased oxygen affinity with that shift to the left. All right, our next conditions we'll look at are decreasing our concentration of CO2 and increasing our pH. So remember, increasing pH means we're lowering our proton concentration. For both of these situations, we're going to see curve 2. This is essentially, we've done the opposite of the Bohr effect. So with our Bohr effect, we said that increasing CO2 and increasing proton concentration would facilitate the oxygen release, shifting the curve to the right. So if we were to decrease these, we'd see the opposite effect, where we would enhance our affinity and get a shift to the left. So we get the shift to the left with that increased affinity. We still have the cooperativity, so we're still a sigmoidal shaped curve. Our last condition there is our increasing our 2,3-BPG concentration. This is something that occurs with increasing altitude. When we increase our concentration of 2,3-BPG, we said this is going to weaken or lower the oxygen affinity, promoting that oxygen release. And so we expect to see a shift to the right with that. So curve 4 represents that increasing concentration of 2,3-BPG. The last curve we'll look at is just revisit our fetal hemoglobin. We've talked about this. Fetal hemoglobin does have a higher affinity for oxygen than adult hemoglobin. So on this curve, we do see that shift to the left, reflecting the higher affinity. We've spoke about how this is what you'd expect, since that maternal hemoglobin is going to need to transfer the oxygen you're going to have to transfer oxygen from the adult hemoglobin onto the fetal hemoglobin. If this affinity were reversed, you would not be able to, the maternal hemoglobin would not be able to transfer oxygen effectively to the fetal hemoglobin. All right, so that wraps up the last of our curves. Hope that was helpful.